Now, the lecture is called Is Learning Feasible? And I am going to address this question in extreme detail from beginning to end. This is the only topic for this lecture. Okay. Now, if you want an outline, it's really a logical flow, but if you want to cluster it into points, we are going to start with a probabilistic situation that is a very simple probabilistic situation, doesn't seem to relate to learning, but it will capture the idea, can we say something outside the sample data that we have? So we are going to answer it in a way that is concrete and where the mathematics is very friendly. And then after that, I'm going to be able to relate that probabilistic situation to learning as we stated. It will take two stages. First, I will just sort of translate the expressions into something that relates to learning, and then we will move forward and make it correspond to real learning. And that's the last one. And then after we do that and we think we are done, we find that there is a serious dilemma that we have, and we will find a solution to that dilemma and then declare victory that indeed learning is feasible in a very particular sense. Okay, so let's start with the experiment that I talked about. Consider the following situation. You have a bin, and the bin has marbles. The marbles are either red or green. Okay, that's what it looks like. And we are going to do an experiment with this bin. And the experiment is to pick a sample from the bin, some marbles. So let's formalize what the probability distribution is. There is a probability of picking a red marble, and let's call it mu. Okay? So now you think of mu as the probability of a red marble. Now, the bin is really just a visual aid to make us relate to the experiment. You can think of this abstractly as a binary experiment. Two outcomes, red or green. Probability of red is mu independently from one point to another. If you want to stick to the bin, you can say the bin has an infinite number of marbles, and the fraction of red marbles is mu, or maybe it has finite number of marbles, and you are going to pick the marbles but replace them. Okay? But the idea now is that every time you reach in the bin, the probability of picking a red marble is mu. That's the rule. Okay? Now, there is a probability of picking a green marble, and what might that be? Okay? That must be 1 minus mu. Okay? So that's the setup. Now, the value of mu is unknown to us. So in spite of the fact that you can look at this particular bin and see, okay, there is less red than green, so mu must be small and all of that, you don't have that advantage in real. The bin is opaque, it's sitting there, and I reach for it like this. Okay? So now that I declare mu is unknown, you probably see where this is going. Okay? Unknown is a famous word from last lecture, and that will be the link to what we have. Okay. Now, we pick n marbles independently, capital N, and I'm using the same notation for capital N, which is the number of data points in learning, deliberately. Okay? So the sample will look like this, and it will have some red and some green. It's a probabilistic situation. And we are going to call the fraction of marbles in the sample. Okay? So this now is a probabilistic quantity. Mu is an unknown constant sitting there. If you pick a sample, someone else picks a sample, you will have a different frequency in sample from the other person, and we are going to call it nu. Now, interestingly enough, nu also should appear in the figure. So it says nu equals fraction of red marbles. So that's where it lies. Okay? Here is a nu. For some reason that I don't understand, the app wouldn't show nu in the figures. Okay? So I decided maybe the app is actually a machine learning expert. It doesn't like things in sample. It only likes things that are real. So it knows that nu is not important. It's not an indication. We are really interested in knowing what's outside. So it kept the mu, but actually deleted the nu. At least that's what we are going to believe for the rest of the lecture. Okay? Now, this is the bin. So now the next step is to ask ourselves the question we asked in machine learning. Does nu, which is the sample frequency, tell us anything about mu, which is the actual frequency in the bin that we are interested in knowing? Okay? The short answer, this is to remind you what it is. The short answer is no. Why? Because the sample can be mostly green, while the bin is mostly red. Anybody doubts that? The thing could have, 90% red, and I pick 100 marbles, and all of them happen to be green. This is possible, correct? So if I ask you what is actually mu, you really don't know from the sample. You don't know anything about the marbles you did not pick. Okay? Well, that's the short answer. The long answer is yes. Okay? Not because no and yes, okay, but just this is more elaborate. We have to really discuss a lot in order to get there. Okay, so why is it yes? Because if you know a little bit about probability, you realize that if the sample is big enough, the sample frequency, which is nu, the mysterious disappearing quantity here, that is likely to be close to mu. Okay? Think of a presidential poll. Okay? There are maybe 100 million or more voters in the US, and you make a poll of 3,000 people. You have 3,000 marbles, so to speak. And you look at the result in the marbles, and you tell me how the 100 million will vote. How the heck did you know that? Okay? So now the statistics come in. That's where the probability plays a role. And the main distinction between the two answers is possible versus probable. In science and in engineering, you go a huge distance by settling for not absolutely certain, but almost certain. It opens a world of possibilities. And this is one of the possibilities that it opens. Okay. So now we know that from a probabilistic point of view, nu does tell me something about mu. The sample frequency tells me something about the bin. So what does it exactly say? So now we go into a mathematical formulation. Okay. Well, in words, it says in a big sample, nu, the sample frequency, should be close to mu, the bin frequency. Okay? So now the symbols that go with that, what is a big sample? Large n, our parameter n. Okay? And how do we say that nu is close to mu? We say that they are within epsilon. Okay? That is our criteria. So now with this in mind, we are going to formalize this. Okay? Now, the formula that I'm going to show you is a formula that is going to stay with us for the rest of the course. I would like you to pay attention, and I'm going to build it gradually. We are going to say that the probability of something is small. Okay? So we're going to say that it's less than or equal to, and hopefully the right-hand side will be a small quantity. Now, if I'm claiming that the probability of something is small, it must be that that thing is a bad event. I don't want it to happen. So we'll have a probability of something bad happening being small. Okay? What is a bad event in the context we are talking about? It is that nu does not approximate mu well. They are not within epsilon of each other. And if you look at it, here you have nu minus mu in absolute value, so that's the difference in absolute value. That happens to be bigger than epsilon. So that's bad, because that tells us that they are further away from our tolerance epsilon. We don't want that to happen. And we would like the probability of that happening to be as small as possible. Well, how small can we guarantee it? Good news, okay? It's e to the minus n. It's a negative exponential. That is great because negative exponentials tend to die very fast. So if you get a bigger sample, this will be diminishingly small probability. So the probability of something bad happens will be very small, and we can claim that indeed nu will be within epsilon from mu, and we will be wrong for a very minute amount of the time. But that's the good news, okay? Now the bad news. Ouch. Epsilon is our tolerance, okay? If you are a very tolerant person, you say, okay, I just want nu and mu to be within, let's say, 0.1. Okay, that's not very much to ask. Now, the price you pay for that is that you plug in the exponent, not epsilon, but epsilon squared. So that becomes 0.01. 0.01 will dampen n significantly, and you lose a lot of the benefit of the negative exponential. And if you are more stringent and you say, okay, I really want mu to be close to mu. I am not fooling around here, okay? So I'm going to pick epsilon to be 10 to the minus 6. Good for you. 10 to the minus 6, pay the price for it. You go here, and now that's 10 to the minus 12. That will completely kill any n you will ever encounter. So the exponent now will be around 0. So this probability will be around 1, if that was the final answer. That's not yet the final answer. So now you know that the probability is less than or equal to 1. Congratulations. You knew that already. Okay? Well, this is almost the formula, but it's not quite. What we need is fairly trivial. We just put 2 here and 2 there. Okay? Now, between you and me, I prefer the original formula better, without the 2's. Okay? However, the formula with the 2's has a distinct advantage of being true. Okay? So we have to settle for that. Okay? Now, that inequality is called Hoeffding's inequality. It is the main inequality we are going to be using in the course. You can look for the proof. It's a basic proof in mathematics. It's not that difficult, but definitely not trivial. And we are going to use it all the way, and this is the same formula that will get us to prove something about the VC dimension. If the buzzword VC dimension means anything to you, it will come from this after a lot of derivation. Okay? So this is the building blocks that you have to really know cold. Okay? So now, if you want to translate the Hoeffding inequality into words, what we have been talking about is that we would like to make the statement mu equals nu. That will be the ultimate. You look at the in-sample frequency, that's the out-of-sample frequency. That's the real frequency out there, okay? But that's not the case, okay? So we actually are making the statement mu equal nu, but we are not making the statement, we are making a PAC statement. And that stands for, this statement is probably, approximately correct. Okay? Probably because of this. This is small, so the probability of violation is small. Approximately because of this. We are not saying that mu equals nu, we are saying that they're close to each other. Okay? And that theme will remain with us in learning. Okay. So we put the glorified Hoeffding's inequality at the top, and we spend a few graph analyzing what it means. In case you forgot what nu and mu are, I put the figure. So mu is the frequency within the bin. This is the unknown quantity that we want to tell. And nu is the disappearing quantity, which happens to be the frequency in the sample you have. Okay. So what about the Hoeffding inequality? Well, the one attraction of this inequality is that it is valid for every n positive integer and every epsilon which is greater than 0. Pick any tolerance you want, and for any number of examples you want, this is true. It's not an asymptotic result. It's the result that holds for every n and epsilon. That's a very attractive proposition for something that has an exponential in it. Okay? Now, Hoeffding inequality belongs to a large class of mathematical laws, which are called the laws of large numbers. Okay? So this is one law of large numbers, one form of it, and there are tons of them. Okay? This happens to be one of the friendliest because it's not asymptotic and happens to have an exponential in it. Okay? Now, one observation here is that if you look at the left-hand side, we are computing this probability. This probability patently depends on mu. Mu appears explicitly in it, and also mu affects the probability distribution of nu. Nu is the sample in n marbles you picked. That's a very simple binomial distribution. You can find the probability that nu equals anything based on the value of mu. So the probability that this quantity, which depends on mu, exceeds epsilon, the probability itself does depend on mu. However, we are not interested in the exact probability. We just want to bound it. And in this case, we are bounding it uniformly. As you see, the right-hand side does not have mu in it. And that gives us a great tool, because now we don't use the quantities that we already declared is unknown. Mu is unknown. It will be a sort of a vicious argument if I go and say that it depends on mu, but I don't know what mu is. Now you know uniformly, regardless of the value of mu could be anything between 0 and 1, and this will still be bounding the deviation of the sample frequency from the real frequency. Okay, that's a good advantage. Now the other point is that there is a trade-off that you can read off the inequality. What is the trade-off? The trade-off is between n and epsilon. Okay. In the typical situation, if we think of n as the number of examples that are given to you, the amount of data, in this case the number of marbles out of the bin, okay, n is usually dictated. Someone comes and gives you a certain resource of examples. Okay. Epsilon is your taste in tolerance. You are very tolerant, you pick epsilon equals 0.5, okay, that would be very easy to satisfy, okay, and if you are very stringent, you can pick epsilon smaller and smaller. Now, because they get multiplied here, okay, the smaller the epsilon is, the bigger the n you need in order to compensate for it and come up with the same level of probability bound, okay? And that makes a lot of sense, okay? If you have more examples, you are more sure that nu and mu will be close together, even closer and closer and closer as you get larger n. So this makes sense. Okay? Finally, it's a subtle point, but it's worth saying. Well, we are making the statement that nu is approximately the same as mu. Okay? And this implies that mu is approximately the same as nu. What is this? The logic here is a little bit subtle. Obviously, I mean, the statement is a tautology, but I'm just making a logical point here. When you run the experiment, you don't know what mu is. Mu is an unknown. It's a constant, okay? The only random fellow in this entire operation is nu. That is what the probability is with respect to. You generate different samples, and you compute the probability. This is the probabilistic thing. This is a happy constant sitting there, albeit unknown, okay? Now, the way you are using the inequality is to infer mu, the sample here, from nu. That is not the cause and effect that actually takes place. The cause and effect is that mu affects nu, not the other way around. But we are using it the other way around, okay? Lucky for us, the form of the probability is symmetric. Therefore, instead of saying that nu tends to be close to mu, which will be the accurate logical statement, mu is there, and nu has a tendency to be close to it. We, instead of that, say that, okay, I know already nu, and now mu tends to be close to nu. That's the logic we are using. Okay?